In this video, we're going to describe the research process and take a look at the descriptive statistics, or statistics that we use to describe our data. There are different types of data analysis that we can do. There are quantitative methods, which we'll be focusing on for this class, and that's testing our theories or testing our research questions or our ideas using numbers. We also have the ability to do qualitative methods research, and that's when we use methods other than numeric to test our theories. Usually it's using language, but it can be using video, pictures, but we can use mixed methods when we want to synthesize the quantitative methods and qualitative methods to test our theories. As I said, for this class we'll be focusing on the quantitative methods. So let's start by taking a look at the research process. Here we have a depiction of a broad overview of the research process. And the way it works is you begin with an observation that you want to understand. And this observation, it could just come from while you're normally going about your business. For example, maybe you're working in the lab of a hospital and you realize that people who have been coming in with lower cholesterol level have said anecdotally that they have been drinking a gallon of unsweet tea each day. So you see that, and then we move on from there, and you take that idea or that observation, and you take from that an idea or a theory that maybe a gallon of iced tea, unsweet tea per day lowers cholesterol. So a theory can perhaps be equated to an explanation. So our thought is that the unsweet tea helps lower cholesterol, and that's the explanation that we provide, the theory that we provide. And this is where our data comes into play. So you take your observation, and we have to collect some relevant data about it. And if we're going to collect relevant data, it has to be data that we can measure something with. And then we analyze the data. So using our depiction so far, we get the data, and that's that we notice that the people that we've taken cholesterol readings on have said that, oh, they drink a gallon of unsweet tea a day, and these are the people that you've noticed have had lower cholesterol readings, or cholesterol readings that lower, and those are your initial observations. From there you generate your theory that, or your explanation that a gallon of unsweet tea per day lowers cholesterol. We take our theory about the iced tea and we turn it into a prediction, and prediction is what we call a hypothesis. So in other words, we predict that for an increase in unsweet tea consumption, you'll get a decrease in our cholesterol level. Now, to get back to our data, in order to do that, we have to identify our variables, and when we did our little prediction there, we identified the unsweet tea consumption, so that would be a volume, how much tea are we consuming, and our cholesterol level would be the other variable that we're looking at there. So then we move on to the next phase, and where we collect data to test the theory. So now we would have to grab a sample of people, or a number of people, to test this theory on, and we would give them a gallon of unsweet tea per day and force them to drink it. And we would measure their cholesterol levels as well, going back to our variables. With these results, we would go ahead and analyze the data and see, well, does the unsweet tea consumption decrease the cholesterol level or not? And we can do that graphing the data, fitting a model, and we'll get into those details a little bit later. But what we'll find is either one of two things. Did the increase in unsweet tea decrease the cholesterol level, or did it not? If it did, great. Now that helps us to identify other ideas or create other ideas that we might want to test. And likewise, if it doesn't, then we might come up with other ideas as well that we want to go ahead and test. And that's the general research process, or the general overview of the research process. I'm going to go through the next few pages rather quickly, so you might want to be ready to pause your video if you want to take notes, because what I'm going to cover is essentially what we just walked through on this page. We're just going to do it in more slides. So I will go through it, and you can reference these slides or make notes as you see fit. I want to pause a moment on this slide because there are a couple of variable concepts that we need to cover on this page. Here we see independent variable and dependent variable. I've put in here also the predictor variable and outcome variable as alternate terms. Now purists will say that there is a difference between independent and predictor and dependent and outcome variable. For our purposes though, it's useful to keep those terms together. An independent variable is what we might think of as what we think is the cause of whatever we think is going on, the phenomenon of interest. It might help to think of this as the independent variable because its value does not depend on any other variable. And the variable that we think is the effect is called the dependent variable. In other words, it's dependent on the independent variable, or the effect that occurs on the dependent variable is based on the impact of the independent variable. In the case of our iced tea experiment, they're closely related to the experimental method that we use. In our example, the cause, or the independent variable, or the unsweet tea, we manipulate by forcing our participants to drink a gallon of unsweet tea per day. In some cases though, we can't manipulate the independent variable, and that's why we can use the term predictor variable. That might be a better alternative to use. At this point, we should look at the different types of levels of measurement for the variables that we're working with. The first level we'll look at is called categorical variables, where the observations, or the objects that are within this variable, are divided into distinct categories. And there could be a measure of binary where there are only two categories. In other words, you're either dead or you're alive. It could be a nominal variable when there are more than two categories, say for example flavors of ice cream, vanilla, chocolate, strawberry. Or if we're working with people, it might be whether somebody is an omnivore, a vegetarian, a vegan. And we also have in that categorical type of variable, we have ordinal level variables as well. The ordinal variable is similar to the nominal variable, but the categories have a logical order. For example, whether people got a fail, a passing, a merit with distinction on their exam. Next we have continuous variables, where the entities get a distinct score. And with the continuous variables, we have interval variables and ratio variables. The interval variables, they have equal intervals on the variable that represent equal differences in the property being measured. For example, you might have the difference between 6 and 8. It's equivalent to the difference between 13 and 15. And then you have ratio variable, which is our highest level of measurement, and that's the one we like to work with, and we'll see why a little bit later. But it has the same characteristics of an interval variable, but the ratios of scores on the scale must also make sense. For example, a score of 16 on an anxiety scale means that the person is, in reality, twice as anxious as someone scoring 8. Perhaps another example that might hit home better is a score of, or a salary of $100,000 per year is twice the amount as someone who makes $50,000 a year. Normally when we talk about levels of measurement, we talk about 4 of the different types of variables or levels of measurement, and those are nominal, ordinal, interval, and ratio. If you just look at what we have on our slide though, you might get an understanding of why. The binary variable actually is more of a subset of the nominal variable because it has the same characteristics. The difference is there are only two categories. You're either dead or you're alive. I'm going to go through a few more slides that are reference slides for when we get into our quantitative analysis 2 level classes. But you can go ahead and keep them for review purposes, or you can go ahead and let the video go through. So if you want to pause it, pause it. Referring back to our research process overview here, we got to the bottom and we talked about graphing the data, fitting a model. Let's go a little bit into detail on the topic as well. So one of the things that we can do is we can analyze data with a histogram. A histogram is a graphic measure of looking at our data, and it's a graph plotting the values of observations on the horizontal axis with a bar showing how many times each value is counted in the data set. A special frequency distribution that we use throughout statistics is called the normal distribution, and some of you may have seen that or heard of that as the bell curve or the bell curve or the normal curve. And the reason that it's called the bell curve is because it looks very normal, very much like a bell to it. And there are some distinctions about, or distinct characteristics about the normal distribution, in that it is symmetrical around the middle point here. Both halves look the same, and we could get into this further, and we will later on, but these red lines that we see here, this red line indicates the normal distribution that's overlaid on this histogram. And the normal distribution is actually asymptotic. The lines don't truly touch the x-axis. They go on out to infinity, but we'll get into that further later. There are three things that I like to know about each data set that I look at, and those are the measure of central tendency, or the point that we find the middle, the shape of the distribution, and the dispersion of the distribution. And we can show that briefly here, and we'll get into it a little bit further. So for this distribution here, we would like to know what the measure of central tendency is. What would be the middle point would be right here, and we would have some value, some score there that we would know what that middle point is. Then we talked about the shape of the distribution. Well, the shape of the distribution here, it's normal and it's symmetrical, but it's possible, and we'll see this later, that that shape could be stretched out more to one side or the other, and it could, in other words, it could be skewed to one side or the other. And then we also talk about what's called kurtosis, which is how flat that curve is. Right now, it's normally peaked, and you can see that this is what would be considered the ideal shape. Finally, I mentioned I like to know about the dispersion, and that's talking about how spread out our data is. So for this example, what this histogram indicates is counts. How many times did we see this value? And then we can see that over here, as we get toward the middle here, we see more and more counts, or frequency is higher in the center than on the outcomes. And we'll talk about different measures of that dispersion later on. So here we talk about skew that we talked about before, kurtosis as well, and you can read the notes on the slide, but essentially the skew is how spread out it is, or is it bunched up to one side or another is probably a better way to put it, because the spread out is the dispersion. And then we have kurtosis, which is how flat or peaked the distribution is. And when the flatter that the distribution is, the lighter that the tails are. And what we refer to are the tails are here. These are the tails of the distribution. And then leptokurtic, and if you think about it as lepto as leaping, your distribution actually gets higher, and it means that your tails are heavier. So here's an indication of skew. And if you think about the skewing, think about the tail. Again, we remember these were called the tails. And on a positive skew, it's pulling the tail to the positive side. On a negative skew, it's pulling the tail to the negative side. So that can help you in remembering the positive and negative skew. So kurtosis, let's try that again. Kurtosis is indicated here on this screen. Now, what we don't show here on our screen is what is considered mesokurtic, or normally distributed distribution is going to have kind of a medium or mesokurtic distribution. So as you can see, as I said, if you think of lepto as leaping, it gets high here, and platykurtic is a little bit flatter than what we had before, and we'll get into that a little bit further as well. I told you I wanted to find out the measure of central tendency as well, and the three that we'll talk about are mode, median, and mean. But for now we'll talk about the mode, and the mode is the most frequently occurring score. If you remember, we talked about the nominal data. So if we had flavors of ice cream, we really can't average the flavors of ice cream. Of course we can mix the flavors together, but that's not what we're talking about here. And it's possible to have a distribution that has two modes. It's also possible to have distribution that has several modes. So in other words, you could have a distribution where you have 2, 3, 4, or more modes, more frequently occurring scores. So they just happen to be tied to be the most frequent. So here is a bimodal distribution, and you can see that these two distributions are about the same, and here you have three that are all about the same. There's a little bit of latitude when you're talking about the bimodal and multimodal distributions, that they do not have to exactly be the same numbers of observations or number of time that they are occurring, but very close to each other. The second measure of central tendency that we're going to look at is called the median. And the median is taking all of our scores, putting them in sequence from lowest to highest, or highest to lowest. Usually it's lowest to highest, and we take the middle value. One thing to keep in mind, though, is if we have an even set of observations or an even numbered set of the data, we won't have a middle point. So what we do there is we take the two middle values, add them together, and divide by 2, and that is our median. So keep in mind, that means that the median might actually be a number that's not a part of your data set. Finally, we'll talk about the mean. And the mean is a measure of central tendency in which we take all of our observations, add them all up together, and we divide by the number of observations that we have. But in order for this to be statistics and make it a little bit more challenging for you, is we use this fancy formula to indicate what I just told you. And we'll probably abbreviate this formula a little bit later to just have the Greek symbol sigma, which is your summation symbol, and then divided by n equals x bar, and x bar indicates the sample mean. And the way we can read this formula, the numerator is the sum of x sub I as x goes from I to n. All of that divided by n equals x bar, or the sample mean. In our example, we have the number of friends of 11 Facebook users. Here are each of the numbers of friends that our Facebook users have. This is the numerator part where we're adding all of these numbers up. Comes to 1045, and we divide that by the number, or n is our number of observations, in this case 11 Facebook users. So we divide that 1045 divided by 11, we get 95. The final thing that I'd like to talk about is the dispersion. Remember, the three things that I like to look at in all my data sets are the shape of the distribution, the measure of central tendency, and the dispersion. One measure of the dispersion is what's called the range. We take the smallest score and we subtract it from the largest. So normally we'll address somebody will say, what is the range of our Facebook users friends numbers, and we'll say, oh, it's between 22 to 234. Statistically, however, the range is actually that difference. So the range is 212 Facebook users, or Facebook friends, excuse me. Another measure of dispersion is the interquartile range, and what we do with the interquartile range is we break up our data set into 4 equal parts. So these are location markers, essentially, of where we split the data. In order to have 4 equal parts, we need 3 dividing points. So we have the lower quartile, sometimes referred to as the first quartile. We have the second quartile, which is referred to as the median. And if you've heard the term percentiles before, that would also be called the 50th percentile. And then we have the upper quartile, or the third quartile. Another form of dispersion is called deviance, and you may have heard the term standard deviation. We're going to work to get to the standard deviation, but deviance is the distance from an observation to the mean. In this case, we're talking about sample data, so we have the x bar is our sample mean. So the deviance is the observation that we have found minus the mean. So for example, if our classroom age mean was 25 years old, and we took one of the students and asked that student what his age was, and we found out that his age was 30, well, the deviance is 30 minus the mean of 25, which is 5. So the deviance would be 5. What we can do is we can take the total deviance, which this summation character looks familiar, I'm sure. Notice though that the n and the I equals 1 are not on the corners, but on top and bottom. That doesn't change the formula explanation. It's just another way to depict it, because we need to make room for the x sub I minus x bar. And so what we're saying with this formula is we're taking the total deviance, which is equal to each observation minus x bar, and adding up those values. Another term for that deviance is error. So we use the term sum of squared errors, SS as it's sometimes indicated, to show the total dispersion from the mean, and we square that, because if we have some values that are negative and some values that are positive, they're going to balance each other out. A good way to explain this is if we are taking our distribution here, and here's our mean, all of these values here, so if we take x minus x bar, so all of these values to the right of the mean are going to create a deviance that's positive, and then all of those that are to the left, since they're already less than the mean, they're going to make a negative value. Because this is symmetrical, in other words, both halves of the distribution on either side of the mean are the same, if we add all of those together, the total deviance is going to be equal to 0. If we instead square each of those differences, those negatives on the left side of the distribution will all become positive values. So that's why we square those values. The challenge with the sum of squared errors, though, is if we keep throwing more and more variables in there, in other words, more and more observations, this number is going to keep getting bigger and bigger and bigger and bigger and bigger. So in other words, the larger the number of observations we have, the larger of our the larger the value of the sum of squared errors is likely to be. So it's not really good for comparing different data sets. Instead, what we do is it's better to work with the average dispersion, known as the variance. And before you get all confused by what's on the screen here, just notice that the numerator here is the same as the sum of squared errors formula. And all we're doing is dividing by n minus 1, or in other words, the number of observations we have minus 1. So in this example here, we have 32,246 divided by 10. So our variance is 3,224 5.6, or 3,224.6. The problem with the variance is that it gives us the measure in units squared, and as you probably remember from elementary school and high school, you always have to remember your units. You always have to state your units. Well, in our example of our Facebook friends, we would have to say that the average error in our data was 3,224.6 friends squared. So the friends are squared also, and it's a little bit tough to explain that or to figure out how to state that when you have friends squared. So what we do is we just take the square root of the variance, and that's known as the standard deviation, and that puts it back into units that we started out with, and in this case would be friends. So our standard deviation is 56.79 friends. Let's go ahead and take a look at what that looks like on a chart or a graphic. Remember, the standard deviation, the variance, on the interquartile range, the range, are all measures of dispersion. In this graphic here, we see that we have different standard deviations. And we can see the data is spread out more when we have a higher standard deviation. So by being standard or standardized, we're able to compare the two data sets and see that this one on the right has data that are spread out further than the data on the left. So it's more dispersed. And if you looked at it under a normal distribution type of curve, you'd see here when we have the different standard deviations. Now when you see it as a Greek symbol sigma, it's referring to the population standard deviation, whereas when we use the S, we're talking about the sample standard deviation. So here in the orange curve, we have a standard deviation of 3.1. So compared to the standard deviation of 5.0 years on the blue distribution, you can see that the 3.1 years data, the orange curve, are less dispersed than the standard deviation of 5.0. And one thing to keep in the back of your mind, just picture this now and see if you had a standard deviation of 0, what might that indicate to you? Well, if you think about it, as the value gets smaller and smaller, it's getting closer and closer. So if the standard deviation was 0, that would mean there's no deviation whatsoever, so everything would be right on the mean. Those would be your only observations, would be the mean. Unrealistic that you're going to find a data set that's like that, but just keep that in mind. Remember the following things that are on the screen here. The variance, the standard deviation, the sum of squares, they all represent the same thing. They just represent it a little bit differently. And they represent the fit of the mean to the data. So we're looking at the mean value. So how well does that mean fit to the data that we have? Like I said before, if we had a standard deviation of 0, that would mean our mean fits the data exactly. All of the data points are right on the mean, or the mean sits on top of all of the data points, whichever way you want to look at that. It also, all of those items like the variance, standard deviation, provide us the variability in the data, and we saw that particularly with the standard deviation, how spread out it is and how variable it is. So it also talks about how, or shows us how well the mean represents the observed data, and it provides us an insight into the error. And by the error, if you remember, when we were doing the sum of squares calculation, which is also feeds into the variance and the standard deviation, we took the x observation, each observation, and subtracted from it the mean value. So that was the deviance, or the error, between each observation and the mean, and that's where the term the error is given. We get some information about the error from our sum of squares, variance, and standard deviation. To this point, we've been talking about the distribution by counting observations, number of observations that we see in a particular value. We can also use the distribution as a probability distribution, and we look at that case of what's the likelihood of an occurrence, or the probability of an occurrence of some event. For example, if we were to look at this distribution and say this is the distribution of the ages of the people in our class, and this is the frequency of passing a test. So this is the younger people we find out are having trouble passing the test, and we have the older people who are having trouble passing the test. It appears that they've only passed the test this many times. So these are counts of time. So let's say we wanted to find out how likely is it that somebody from, let's say the age is down here, this is age 10, 20, 30, 40, 50. So what is the likelihood that somebody between the age of 10 and say 18 are going to pass the exam? Well, that's this area right in here. So we say it's not very likely. Well, how likely is it that somebody from the age of say 25 to 35 is going to pass the test? Well, that would be about from here to here and would encompass all of these observations here. And so in this case we could say it's very likely that they're going to pass the test. And so far as I'm talking about likelihood or probability, I'm talking in relative terms. This is less likely, this is more likely. But we can be more precise than that. We can actually put values to that by doing calculations or having our computer program do that. So let's go back to our curve that has the probabilities on. Technically, this isn't really any different from the other distribution, except we don't have the histogram. It's because we don't have actual frequency counts or number of observations. Now we're talking about probabilities or how likely something occurs. And when we're talking about probability distributions, the entire distribution, remember that this normal curve is what's called asymptotic. It doesn't actually in reality touch the x-axis. It goes out to infinity on both sides. But the entire distribution is all possible probabilities, or 100% of the probabilities, otherwise known as 1.0. And we know certain things about the distribution that we'll get to a little bit later, but for now we can see if something is over in this blue shaded area, it's a smaller portion than the larger portion, which is the white area, so it's less likely to occur if it happens in this blue shaded area than if it happens in the white shaded area. And we'll get into it a little bit further down where we actually put number values to this, and we'll say if we're at this area, this is less than 3% chance that this would occur, or some other value. The challenge with the normal distribution or the probability distributions is the same as we were talking about before. You can have different standard deviations and you can have different mean values, or you can have both different this is where we have different standard deviations. Here we have different mean values, and here we have different mean values and different standard deviations. So if you're looking at these three here, how do you really compare them? It's challenging. So what we can do is we could take any normal distribution and convert it into what's called a standard normal distribution, so that it doesn't fry our brains trying to calculate different things for each of these different family of distribution. And that standard normal distribution has a mean of 0 and a standard deviation of 1. So all of these different these different distributions, we can convert them into a standard normal distribution, then we can compare them easily. As I said, any data set can be converted into a data set that has a mean of 0 and a standard deviation of 1. And the first thing that we do is we center the data around 0, and to do that we could take each score or each observation, x, and subtract from it the mean of all the scores, the x bar. That's what we're doing right here in the numerator. To convert the data, or to ensure that the data have a standard deviation of 1, we divide the resulting score by the standard deviation, which is indicated by the s, which we recently encountered. And now the resulting scores are denoted by the letter z, and they're known as z-scores, sometimes known as z-values. So z-scores, z-values are the same thing. And there are certain properties that you have of the z-score, and that is 1.96. A z-score of 1.96 cuts off the top 2.5% of the distribution. Negative 1.96 cuts off the bottom 2.5% of the distribution. Because of that, 95% of the z-scores, and that's about 95% of the z-scores, lie between negative 1.96 and positive 1.96. And about 99% of the z-scores lie between negative 2.58 and positive 2.58 standard deviations, and 99.9% of them lie in between negative 3.29 and positive 3.29 standard deviation. And here we can see one of the depictions that we were talking about here. 95% of the scores lie between negative 1.96 z and positive 1.96 z value. And that's all for this video. Hope you enjoyed it, and I hope it was helpful.